Hello everyone and welcome to the last lesson, Lesson 8 of the AP Calculus AB/1 summer course. Today we're going to be talking about an introduction to integrals. So I guess it makes sense to start about what is an integral. And so we already talked about this, I guess at the very first lesson. It was one of the very first things I said at all, is I explained what limits, derivatives, and integrals are. Well, today it looks like we finally made it to the last leg of our journey, which is integrals. And if you remember what I said back then, and maybe you can tell by this picture, when we talk about integrals, we are talking about area, specifically area under a curve. As you can see here in this example, all the gray area is the, area under my function. We'll call it f of x, or whatever it is. And when I say under the curve, I mean it's the area bounded by, obviously, the function, and then in this case, the x-axis. So as you can see here, that's what integrals are. It's area. And we have a bunch of different ways to find this area. And just like how back in the day when we started talking about derivatives and how we said derivatives were slope, I don't know if you remember this, but we talked about ways of basically getting down to how we found the slope in the first place. You could even say that, if you remember what we did, the y2 minus y1 over x2 minus x1 equation, that was just a way to approximate slope. We're going to start off today with approximating this area. Because I think you would agree with me that you look at this and I would say, I don't know how to find this area. The only shapes I know how to find the area of are triangles, circles, rectangles, stuff like that. And I guess you could say, hey, this, kind of looks like a triangle here. And, this kind of looks like a semicircle there. And basically what I'm going to tell you is, yes, you can do those weird shapes. But as it turns out, the best thing to do, at least right now, today, is the Riemann sum. And the Riemann sum is going to use rectangles. So here's an example on my screen right here. As you can see, if you include a lot of rectangles, you get a pretty good approximation of what the graph is going to look like. Now, obviously, as you can see here, all of these rectangles are bounded on the left side. And on the next page, we're going to see you can do a left Riemann sum, is what this is called. I'll call it a left Riemann sum. And the reason why is because all of the rectangles are bounded by the left side. And you can sit here and you can say, hey, this is a pretty good approximation, but Dan, I bet I could get an even better approximation if I used smaller, thinner rectangles. And you're exactly right, and that's what the next two pictures show. As you get thinner and thinner rectangles, you're going to get a better and better approximation for your area until finally you can't go any thinner. In other words, what we're doing right here is we are doing the limit as, we'll call it delta x, which is the change in x. As delta x approaches 0, this is what an integral is. It's actually funny because I've done the approximation and the limit before. We actually all did. It was called the limit definition of the derivative. I believe we covered it in week 2 or week 3, I forget. But it's funny because today was the first time ever with another student who's in college right now. She's taking a summer course. I actually did this exact thing with the limit, except with the integrals. And it's funny because since I've never seen a question like that in my life, I actually didn't know how to do it, which is very rare that I see a problem that I don't know how to do. So that basically means I have to learn it, just like how you are going to learn everything that you don't know how to do. And then the more time you spend studying, the smarter you get, the more stuff you know. So anyways, as I promised, there are 3 kinds of Riemann sums we're going to be looking at today. The first is the left Riemann sum that I mentioned earlier. Next is the right Riemann sum, where you can see all the rectangles are hinged at the right end point of the rectangle. And then the last one is the midpoint Riemann sum, which uses the middle point. Now, I'm not going to tell you that one's better than the other, although generally speaking, the best is usually a midpoint Riemann sum. That's just, it kind of looks like it anyway. But we're not going to be talking about how good of an estimate they are. In other classes, when you actually take calculus, you can actually see exactly how good or how bad this approximation is. You can even tell me if it's an overestimate or an underestimate. But for now, we're just going to find the estimates. I'm not going to ask you to evaluate them. I'm not going to ask you to judge them and find the error, although you could. Now let's talk about how you calculate the Riemann sum, which is just basically adding a bunch of rectangles together. So just real quick, area of a rectangle, hopefully you know this, it's length times width. And the width in this case is going to be, we call it delta x. I'm going to call it w for width though, just so you know. I'm going to say w equals b minus a over n. where B is the higher number, A is the lower number, and N is going to be the number of rectangles you have. And I explain that basically in this, this text right here. So if you want to write it down, you can. B is the higher number, A is the lower number, N is the number of rectangles. What do I mean by the higher number and the lower number? I should explain that. If I go back up to this example, let's look at the left Riemann sum. It looks like this is starting at x equals A, so A is the lower point. We end at x equals B. B is the higher point on the x-axis. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 rectangles. N equals 15 in that case. So that's how you can find the width for this example. So now let's keep going. As I mentioned, we have a width. Then that begs the question, what's the length going to be? And the length is going to be the actual value of the function, for instance, f of x. That's how you're going to find the length. It's f of x. The width you're going to find by just plugging in this formula right here. And then you're going to add all the areas together. And don't worry, I have this very nice formula right here, which in my opinion is impossible to read for you guys. So I'm going to give you a better equation. And basically, I discovered this method earlier this summer, so it was too late for me to put it in the study guide, but at least I can talk about it now. So the first step for solving Riemann sum problems is I want you to list out the numbers from A to B, in other words, the lowest point to the highest point, counting by the width W. List out the numbers A to B, counting by width. And I'll do an example at the very end here. Step two, you need to figure out if you're doing a left, a right, or a midpoint Riemann sum. Because obviously the three are going to do different things. And then finally, step 3, you're going to plug in each value of x and then multiply by the width. Plug in each value of x into the function and then multiply by the width. So in other words, the width is a constant. And if I were to give an example of this, and hopefully you have space in the margins somewhere, or maybe even on the next page. If I were to give an example, let's say my width is 0.5, just as an example. A is, let's just say 1, and B equals 4. Then what I would do is, I would start at A, 1, and I would go up by the width each time. So like, I'm counting by 0.5. So the first number is 1, then 1.5, then 2, then 2.5, then 3, then 3.5, and then finally 4. And that's how I count. And basically what I would say is if you want the left Riemann sum, you're going to use these, basically all the values on the left except the last one. That's for the left Riemann sum. And then for the right Riemann sum, you're going to use all the right values except for the leftmost one. And then I'm sure you're wondering, what do I do for the midpoint Riemann sum? Don't worry, I'll talk about that just on the next page. But any questions on that, first of all? Okay, so looks like we're doing good so far, hopefully. So for the first example here, you'll notice it's a table of values. Does it matter that it's a table versus an actual function? No, it doesn't. If in my opinion, the table's a little easier than the function. You'll see why. It's less work. But here's what I'm going to do. First thing I do is I see that A is, well, I'm going to read the problem to you guys. Use the table of values of x for f of x to calculate the left, right, and midpoint Riemann sums over the interval from 1 to 9 using 4 rectangles. Show each Riemann sum using the plots provided. So first we're going to start with the left. And when I do the left, the first thing I'm going to do is I'm starting at 1, ending at 9, and it says 4 rectangles, right? So I got to find my width, first of all. Width is equal to b minus a, so 9 minus 1, over n, the number of rectangles. So it looks like the width is 8 over 4, which is 2. And again, if I want the left Riemann sum, I'm going to start at 1. I'm going to count by 2 because that was my width. So it's 1, then 3, then 5, then 7, then 9. And if I want the left Riemann sum, I'm doing the left 4 numbers, 1, 2, 3, 4. Or should I say 1, 3, 5, 7. And now, if I want to use these values, first, the area is equal to, watch this, 2 times the quantity. And the reason why I'm saying times the quantity is because that is what the width is, and it's going to be distributed to each of these terms in the middle. And then I just have to look at 1, 3, 5, and 7. So for instance, at 1, the y value, or f of x, is 2, plus at 3, the y value is 3, plus at 5, the y value is 1, and at 7, the y value is 1. And if I do this in a calculator or just do it with mental math, I'm going to get my area. 2 plus 3 plus 1 plus 1 is 7. 2 times 7 is 14. The area is going to be 14. And that's an approximation for the area under this curve. Now, how would I draw that Riemann sum? Here's how. Notice all of my rectangles are hinged at the left endpoint. So in other words, I'm going to go from left to right. I'm going to start with this rectangle that only gets this high because it stops at the top left point. And here's my area. And you can shade that in if you want, because remember, that's what we're doing. And then the next point goes all the way up here to that point right there. Goes to the right and then down. Oh shoot, I just realized I made this, it's fine, I did the same thing when I was practicing this. My width is 2, right? So doing this would be wrong, because right now my width of the rectangles is 1. So I have to erase this, I apologize. Sorry. Basically what I'm saying is I have to go from 1 to 3, because that gives me a width of 1. So this is actually my first rectangle. Then the next rectangle is going to be from 3 to 5. Again, hinged at the left end point. So that's going to look like that. There's my area there. Then the next one at 5 to 7, it goes up this high, goes right and then down. And then from 7 to 9, it's going to look very similar. It's going to look like that. Any questions on my approximation? On how I drew it? Okay. So that's it for the left Riemann sum. Next we're going to do the right Riemann sum. The right Riemann sum is very similar. You'll notice that it starts out the same way. Width is still 2. It's going to be the exact same math. The numbers are 1, 3, 5, 7, and 9. The only thing that's different is I'm choosing these numbers, 3, 5, 7, and 9. So then going back to my table, I'm not going to use 1, so I'll erase that. Instead, I'm using 9. And so when I put these together for my right Riemann sum, it's going to be 3 plus 1 plus 1 plus 2. Because remember, it's all the y values. So it's 2 times the quantity, 3 plus 1 plus 1 plus 2, because those are the y values. It's going to be 2 times 7. And again, we get 14. Looks like both the left and the right Riemann sum were both 14. That is very rare. That normally does not happen. But any questions on that one? Okay, now we still need to draw the rectangles. If I want the right Riemann sum, I'm actually going to start from the right. And the reason why is because I want them to be hinged on the right endpoints. So let me show you what I mean. I'll even color code it a different color. So basically, starting here, drawing my rectangle, going from 9 to 7. It's going to be that high. And again, it's hinged at my right endpoint. Next, I'm going to do 7 to 5. That's going to be this rectangle right there. Draw the area. Next is from 5 to 3, so that's going to be this area right there. And then last, I have from 3 to 1. So going all the way up there, and then going down, and I'm hinged right there. Yep. So there's my area, and there's my rectangles. Any questions with that one? Okay, then there's only one more to do, the midpoint. So for the midpoint, I know I didn't say it yet, but here's how you do the midpoint. Midpoint. First of all, the initial strategy stays the same. Width equals 2, 1, 3, 5, 7, 9. That's nice. All that's the same. What's different is for the midpoint, I go in between. Let me explain. What's in between 1 and 3? Obviously, it's 2. Between 3 and 5 is 4. Between 5 and 7 is 6. And between 7 and 9 is 8. There are my 4 numbers that I'm going to use for the midpoint. And conveniently enough, if you look back at your chart, you're going to see that I have 2, 4, 6, and 8 all here. Here's 2, 4, 6, 8. I can do it. If you didn't have these values on the chart, There's kind of a way you can do it. I'm not going to tell you how to do it because I'm not even sure if I want you to be learning that, especially at this early on. But all the examples you're going to see in the homework and today, we have the numbers, so it's going to be fine. So anyways, what I'm saying for the midpoint is it's going to be a width of 2 times, not 2 plus 4 plus 6 plus 8. I actually have to look at the y values. 3 plus 2 plus 1/2 plus 2. 3 plus 2 plus 1/2 plus 2. If I distribute the 2 everywhere, it's going to be 6 plus 4 plus 1 plus 2 because I distributed the 2. And then adding these all up, I'm going to get 10, 11, 13. And 13 is the area for my midpoint. Or did I do that wrong? 10, 11, 13. I did do that wrong. Silly me. That last one isn't 2, it's 4, because 2 times 2 is 4. So it's actually 15. 15 is the area for that one. And now how would I draw that? Well, basically, all your rectangles are hinged at the midpoint. So for instance, the first one's at 2, and it goes from 1 to 3. So from 1 to 3, I've got that rectangle right there. You'll notice my green rectangle is hinged. And I keep using that word hinged. I'm hoping you know what I mean. I mean that it's fixed at that point. It's got the same height as that point. There's my first rectangle. Next is from 3 to 5. I'm going to be using 4 as my height right there. Here's 3 to 5. There's my area. Next is from 5 to 7. It's going to be at the height 6. It's going to be that rectangle right there. And then the last one, 7 to 9, hinged at 8. Going all the way to 8 and then going back down. And there's my area. Now, if you want to know the truth about which one's the best approximation, left, right, or midpoint in this case, the answer is I have no idea because I don't have the area of this function because there's no way of actually finding the exact area. The best we can do is an approximation, and that's all we're going to do when we have a Riemann sum. And you may be wondering, why is the Riemann sum important? Well, basically, it's important because it was the introduction before we actually found the area using the integral. The integral, also known as the antiderivative, which I'm going to be talking a little bit about on like the next page probably. But we're not going to be doing integrals like formally. In other words, we spent the first, I don't know how many lessons, like lessons 3, 4, 5, and 7 probably. I forget which exact lessons we were learning our rules of derivatives. But we spent like almost all the summer talking about the rules of derivatives, basically. There's also rules for integrals. And we're not going to be talking about those today, but you will when you actually take calculus. Today it's all about like, whenever you first learn about integrals, you learn about Riemann sums first. You're going to learn about area first. You're going to be learning about everything but the integral. In the same way that if you want to go snowboarding on a mountain, you got to learn how to, just get on the board first before you can actually go down the mountain. And we're just not going to get there in an hour today. So that's why we're not going to do that. Anyways, enough of me blabbering. Let's do another example here. This one's going to be an actual Riemann sum. In other words, we have a function. The good news is it is exactly the same thing we just did. I'm starting with width equals b minus a over n. So higher number's 2 minus negative 1. Divided by the number of rectangles, which in this case it says 3. So divide by 3. 2 minus negative 1 is the same thing as 2 plus 1, so it's 3 over 3, which is just 1. The width is 1. And that means when I do my left Riemann sum, first thing I do, I got to pick my numbers. Well, I don't really pick my numbers, I determine them. But it's going to be lowest number, negative 1, and then I count by 1 each time, because that was my width. It's going to be negative 1, 0, 1, and 2. And so what that means is when I want my left, I'm going to be using these three numbers right here. And when I say use these three numbers, I'm going to be plugging them into my function x cubed. So let me show you from a notation point what I'm going to write. I'm going to write the width, which is 1, times the quantity, f of negative 1 plus f of 0 plus f of 1. That's the left Riemann sum. And if you plug in negative 1 cubed is negative 1, plus 0 cubed is 0, plus 1 cubed is 1. You plug this in a calculator, or even just do a little bit of mental math, you're going to get an area of 0. Now, how is it possible to get an area of 0? How is that even possible? The answer is, and let me even scroll up to this example right here. It was literally the first page. One thing you ought to know is that if your area is above the x-axis, like here and here, your area is positive. And if your area is below the x-axis, well, then we would say that area is negative. And so that's how you can have a positive and negative area. Or even a zero area means that the positive and negative cancels out. Isn't that so cool? So that's it for the first one, for the left Riemann sum. Now let's find the right Riemann sum. For the right Riemann sum, I'm sure you know how to do it, but this is my show, and I will be taking full credit. So I'll be doing this one too. For the right Riemann sum, again, same thing. You're going to write out your numbers, negative 1, 0, 1, and 2. But this time we're picking the right three numbers for the right Riemann sum. And so this time the area is going to be the width, which is 1, times f of 0 plus f of 1 plus f of 2. And if you think about it, like almost all the numbers are going to be the same. Like f of 0 we already did, it was 0. F of 1 we already did, it was 1. And that means f of 2 is the only one we have to figure out. It's just going to be 2 cubed, which is 8. So then you plug this in a calculator and you'll get a final answer of 9. And so there we go. Now if you want, you can find the midpoint Riemann sum as well. And if you want the midpoint, all you got to do is ask yourself, well, what's in between negative 1 and 0? It's negative 1/2. In between 0 and 1 is 1/2. And in between 1 and 2 is 3/2. And I'm not going to spend time doing this because it's basically the same idea. And you have to like cube this number, and I don't feel like doing that. But it's the exact same thing, where you're going to be choosing the numbers in the middle of these choices and then just plugging them into the function and adding them together. And we will be doing practice of the midpoint sum later today, so that's why also I don't want to do it right now. But any questions before we get into the actual integral? Okay. Now, as I mentioned, we're not actually doing integrals today. Then why am I showing you integral notation? It's because there's a way you can find integrals without taking the antiderivative. And just to be clear, an antiderivative is the opposite of derivative. So in other words, let me just show you, because I'm tired of alluding to it and not explaining it. I'm sure you want to know. Let me tell you. If you have the integral of x cubed, for instance, the derivative of x cubed, we would say it's 3x squared, right? Why? Because you move the 3 out in front and then you subtract 1 from the exponent. An antiderivative is literally the opposite thing in the opposite order. In other words, if I want the integral of this, I add 1 to the power, so like x to the 4th, and then instead of multiplying by 3, I divide by 4. And if you look at this, x to the 4th over 4, and you take the derivative of this, if you take the derivative of this, you get 4x cubed over 4, the 4's cancel, and you get x cubed. And wasn't that the original problem? Yes, it was. So the cool thing is once you learn antiderivatives, you now have a way to check your work. It's by taking the derivative. Isn't that amazing? And the answer is yes. So that is what we're not going to be doing today, although it's not that hard. This is like the easiest example you ever see. It's just the power rule. As you know, we have product rule, quotient rule, chain rule, all things that do not exist in integrals. So it wouldn't even make sense to talk about them when we talk about antiderivatives. And if you're wondering how do you deal with quotient rule, product rule, and chain rule, that's something called the U substitution. And if you want to find more about that, you can go to my website and check out my online course. But if not, it doesn't matter. We're just going over very, very, very basics today. Starting with the integral notation. So first of all, this right here, if you've ever seen that in math, because I remember back when I was in like 7th grade, you can turn to the back of your like Algebra 1 textbook, and even especially like your pre-calculus textbooks, maybe not your algebra textbooks, but you look at the back of your pre-calc textbooks even, you're probably going to see these symbols here. This symbol that looks like a really long S. And that symbol is the integral symbol. And what all it means is take the integral. In other words, integral means area. It means find the area from A to B of your function. And then the dx, well, remember this. Didn't we say delta x was the width? And delta x is just another word for dx. And do I want to explain why? Okay, fine. Delta x is just like your x distance. In other words, all your rectangles have whatever width they have, right? Each of these rectangles has a width of delta x. Dx is specifically an I cannot spell this right. I'm just going to say the word. An infinitesimally small width. In other words, it's like having a width of 0. But it's not 0 because it's 0.000000001. Actually smaller than that. Infinitely smaller than that. But still bigger than 0. basically, what do you need to know about dx? Here's what you need to know about dx. You start a sentence with a capital letter. That's what the integral symbol is. You end a sentence with a punctuation mark. Dx is your punctuation mark, okay? So if you start a sentence with a capital letter, in other words, if you have an integral, then you better end your integral with a dx, or else it's like leaving a period, forgetting a period at the end of your sentence. Okay, so that's it for the notation. And the way you would read this is you would say the integral from a to b of f of x dx. The integral of a to b of f of x dx. In other words, you read the lower number first because remember, that's where you're starting and you end at b. Okay, so with that, we're going to be spending the rest of today, well, I shouldn't say that. The last new thing we're going to learn today is finding integrals using geometry. Let me show you how we do that. So first we have the integral from 0 to 5 of 3 dx. Remember, what this is saying is f of x, your function, is just 3. And hopefully you know how to graph 3. If you don't, I don't know how you made it to calculus, but here's a function, x and y. F of x equals 3 is just a horizontal line at 3. And when I want the integral from 0 to 5, here's 0, here's 5, I'm really saying I want the area under this graph from here to here. And I really hope you know that this is just a rectangle. And of course, rectangles have an area of length times width. And it looks like my length is 5 and my width is 3. So it looks like the integral and the answer to my question is 15. In other words, the integral from 0 to 3 of 3 dx, integral from 0 to 5. Integral of 0 to 5 of 3 dx is 15. The area is 15. So in other words, the rest of the problems we're going to be doing today that are not Riemann sums, they are basically going to ask, hey, can you look at the integral notation, turn it into a function, and then find the area? And the 3 shapes we're going to be looking at today are rectangles, triangles, and semicircles. This was obviously the rectangle. And hopefully you know that area equation. If I ask my college students, about 2/3 of my college students know the area of a rectangle, at least immediately. A lot of them spend like 10 seconds thinking about it, which always amuses me. And then for the triangle equation, which of course is area equals 1/2 base times height, which you've probably known since 2nd grade, about 50% of my college students know what that is. And before the pandemic, I would say it was closer to 90%. So I would say the pandemic really did a number on you guys. But luckily, that doesn't affect me. I graduated before that happened, so that's your problem, not mine. Anyways, for this one, integral from -1 to 3 of x minus 1 dx. First thing I'm going to do is I'm going to graph this thing. And I know x minus 1 is just going to be a linear line with a y-intercept at -1 and a slope of 1. And this doesn't have to be perfect, right? Like I can graph something like this and I can graph something like this. But I better get my tick marks right, which in other words, here's -1, here's +1, here's +2, here's +3. I stop at 3, right? And then what y value is that? Well, the y value is going to be 2. How do I know that? Well, it's because if I plug in 3 for x, 3 minus 1 is 2, so that's 2. If I go the other way to, let's say, -1, and I plug in -1 for x, I'm going to get -2 down here. So now I say I have 2 rectangles. I'm sorry, not rectangles, triangles. The first triangle, right here, is going to be 1/2 base times height. So 1/2 times the base, which is 2, because it goes from -1 to +1. That's a distance of 2. And then times the height. The height, careful, is -2. The height is -2. And the reason why it's negative, obviously, is because it's below the x-axis. The 1/2 and the 2 cancel out. You get an area of -2 for the first triangle. And then for the next triangle, it's this area right here. And that's going to, again, be area equals 1/2 base times height. So 1/2 times the base this time is 2 again. And the height looks like it's also 2. And so I would say this area is 2. And if I want to find the total area, or the total integral from -1 to 3 of x minus 1 dx, I just need to add these areas together. -2 plus 2 equals 0. There's your answer. The answer is 0. The area perfectly cancels itself. Any questions on that one? And now for one more example. This is going to be the semicircle example. It's worth knowing this is the equation of a semicircle. It looks like a square root of some number minus x squared. It's always some number minus x squared. So now I'm going to graph this. And I want to graph it from -2 to 2. And if I think about what x values here are the ones that are going to matter, in other words, what are going to, I guess, define this function, my recommendation to you would plug in 2 and -2 for x. Because if you plug in +2, you're going to get square root of 4 minus 4, which is 0. In other words, I have the coordinate point 2, 0 right there. If I plug in -2 over here, well, then I'm going to get 4 minus a negative number squared, still positive. So 4 minus 4, I get 0 again, right there. And then if I plug in 0, it's the square root of 4 minus 0, and the square root of 4 is 2. And that's why this is the graph of a semicircle, because no matter where you go, it's always going to have a radius of 2. The radius is 2. Or you could have got that from the beginning. As soon as you saw that 4, you take the square root of it. That's going to be the radius every time. And so now if I want the area from -2 to +2 of this shape, which again is a semicircle, who here knows the area of a circle? Oh, sorry, I meant semicircle. Who knows the area of a semicircle?
It's going to be half pi r squared.
Yes, and fun fact, if I told you that 90% of my students don't know that formula, I would be being nice to them. It's probably close to 95%. Anyways, don't go to college. You clearly get dumber. Just kidding. Or at least, look, I'm not going to say which colleges my students come from. All I'm going to say is that they're business majors. Nothing wrong with business majors, but they clearly do not remember semicircle equations like I do. So it's 1/2 times pi times 2 squared. You plug that in a calculator, you're going to get 2 pi as your answer. 2 pi is the area of your semicircle. Any questions there? Okay, then with that, the rest of today, we're going to be doing example problems. So for this next one, we're going to find the right, left, and midpoint Riemann sums of f of x equals 2x minus 1 over the interval from 0 to 6 using 3 evenly spaced rectangles. I'm going to give you about a minute to do this on your own. I want you to get the left Riemann sum. We're going to go left, right, center. Okay, left, right, midpoint. I want you to do the left Riemann sum on your own, and once you get that, you can either stop or keep going. I'm going to give you about a minute to do that. If you're watching the recording, just pause the video, and then we're going to cover it together, and we're going to talk about it. So go ahead and give it a try. And time. So let's see how we'd find the left Riemann sum. First, I'm hoping you found the width. The width is just 6 minus 0 over, we want 3 rectangles, so 3. 6 over 3 is 2. The width is 2. So that means when I count my numbers, I start at 0 and I count by 2. So it's 0, 2, 4, 6. And if I want the left Riemann sum, it's going to be these 3 numbers on the left, and that's what I'm going to be plugging in my formula. So the area is equal to, it's going to be width 2 times f of 0 plus f of 2 plus f of 4. And so that's going to be f of 0 is -1. When I plug in 2 there, I'm going to get 3, so plus 3. And then when I plug in 4, I'm going to get 2 times 4 is 8, minus 1, 7. So it looks like I get 2 times 2 plus 7, 9. Looks like my left Riemann sum is 18. Any questions there? Okay. Next, I'm going to be going through the right and the midpoint Riemann sums, not because I don't trust you, but simply because we've got a lot more examples to go. So, for the right Riemann sum, again, same idea. The width is 2, and it's the numbers 0, 2, 4, and 6. And this time I choose the right 3 numbers. And when I plug it in this time, it's going to be 2 times, when I plug in 2, I'm going to get 3. When I plug in 4, I'm going to get 7. And when I plug in 6, I'm going to get 11. And of course, I trust you. You can plug in 2x minus 1. I'm sure you can do that pretty easily. But when I plug this in my calculator, I'm going to get a final answer of 42 this time. Significantly bigger. And then for the very last one, the midpoint. Who remembers how to do the midpoint?
Don't you have to have like take the average of like the consecutive points? Like if you have 1, 2, 3, 4, then it's like 1.5, 2.5, 3.5.
Exactly. And so then here the midpoint is 1, 3, 5. And now that's what I'm plugging in my function. So it's going to be 2 times, when I plug in x equals 1, I'm going to get 1, plus when I plug in 3, I'm going to get 5, and when I plug in 5, I'm going to get 9. Exactly. And so then that's going to be 2 times 15, and so then that gives me a final answer of 30. So the midpoint Riemann sum is 30, which is in between the left and the right Riemann sum. It's not always in between, obviously, but it was this time. So are there any questions on that one? Okay. Now the next one's going to be significantly harder, and you'll see why in a minute. So go ahead and try this one on your own. Again, just try the left. I'm going to give you enough time to do the left, and then we'll go over the left, right, and midpoint. So go ahead. And I'll let you use a calculator for this one. And time's up. So maybe you realize why this one's hard. It's because there's fractions involved. And if you didn't have a fraction, then you should be saying, uh-oh. So first the width, high number minus the low number, divided by 3. And that's going to be 4/3. Now, how on earth are we going to count this? Well, here's my advice. You start at -1 and then you count by 4/3, right? Well, why deal with -1 when instead you can deal with -3/3, and now you've got a common denominator. So -3/3 plus 4/3, that gets you 1/3. And then after that, you'll get 5/3. And then another 4 gets you to 9/3. And I stop there because 9/3 is 3, and that's my higher number. So then if I want the left Riemann sum, I'm going to be using these 3 numbers on the left. And I don't have to write -3/3. I can just write -1. That's fine. As a matter of fact, I'll replace it now that I got my numbers. So that's -1, and 9/3 is 3. Okay. So now I just got to plug those into my function, -x² plus 3. And so my area is going to be 4/3 times, when I plug in -1 here, it's going to be -1 squared plus 3. And it only gets harder from there. The next one is plus -1/3 squared. Got to be careful with these parentheses. It's ridiculous. -1/3 squared plus 3. And then the next one is plus -5/3 squared plus 3. And then the last one is -3 squared plus 3. And luckily I plugged this in my calculator earlier today. And if you do the same, you'll get some crazy decimal. As a fraction, it ends up being 184/27. And there's my answer for the first one. Any questions there? Okay. Now for the right Riemann sum, we're going to be doing basically the same idea, except this time we're using the right 3 numbers. If it was -1, 1/3, 5/3, and 9/3, I'm going to be choosing these numbers. Oh, and 9/3 was really 3. So in other words, it's going to be 4/3 is my width, times, plugging in 1/3, which we actually already did. It's going to be -1/9 plus 3, because that's what I get when I plug in to -x² plus 3. The next one's going to be -25/9 plus 3. And then the last one's going to be just, -9 plus 3, which that's the only one that's easy to solve. Anyways, I plugged this in a calculator earlier. I got a fraction, -104/27. And there's my right Riemann sum. Again, not crazy difficult. What's going to be more annoying, the most annoying, is the midpoint Riemann sum. And the midpoint is going to be this. First, writing out my numbers, I'm going to go back to fraction because clearly that will be easier. -3/3, 1/3, 5/3, and 9/3. And now if I want to go in between these two numbers, if I want to find the average of them, obviously this is getting pretty tough. If you want my advice, whenever you get stuck on an average, what you should do is you should add the numbers together and divide by 2. For instance, negative 3/3 plus 1/3 divided by 2. It's going to be negative 2/3 over 2, which is the same thing as negative 1/3. And that's exactly what this is going to be here. It's going to be negative 1/3. If you do the same thing for the next number, it's going to be 3/3 or 1. And then doing the same thing for the last one, you're going to get, that's 14/3, so then 7/3. So that's how you find your midpoints. And now you just got to plug it in the function. So for instance, it's going to be, again, the width, 4/3, times the quantity. When you plug in negative 1/3, you're going to get negative 1/9 plus 3. When you plug in 3/3 or 1, you're just going to get negative 1 plus 3. And then for the last one, it's going to be, when you plug in 7/3, you're going to get negative 49 over 9 plus 3. And finally, if you plug that in a calculator, you'll get a final fraction of 88 over 27. And that's how you do these problems. Any questions? Okay, then we're almost done today. Just the last few problems we ever have together are going to be some integrals that we use the geometric formula for area, aka rectangles, triangles, and semicircles. So for number 3, we got to graph x over 2. It's not the most fun function to graph, but just remember, x over 2, in case you don't know what that is, it's the same thing as 1/2 x plus 0. And the reason why I'm saying plus 0 is because the y-intercept is 0, and y equals mx plus b is really easy to graph. So in other words, I'm graphing a slope of 1/2 from negative 3 to positive 1. So 1, 2, 3, positive 1. Positive 1, I get to 1/2. 0 is 0. Then it's going to be, if that's negative 1, it's negative 1/2, negative 1. And if this is negative 2, I get all the way down to negative 3/2. In other words, this y value right here is negative 3/2. And again, the way I know that for sure is because you can plug in negative 3 into the function. You're going to get negative 3 over 2, aren't you? Same thing goes for positive 1. You plug in positive 1, you're going to get 1/2 right there. And so now I got to find the area of these two triangles here and there. So starting with the negative one, the negative triangle, looks like it's going to be an area of 1/2 times the base, which is 3, times the height, negative 3/2. Looks like I get an area of negative 9 over 4. And then for the other one, for that little guy right there, well, that area is just going to be 1/2 times the base, which is only 1, and then the height is 1/2. Looks like I get 1/4 for that area. Then if I want to find the total area, I just got to take negative 9/4, add 1/4. I'll get negative 8/4, and it looks like my integral, or my area, is negative 2. And that's it for that one. So we only got one problem left. Why don't you try it on your own? I'll give you about a minute for that. Probably closer to 45 seconds. Go ahead. And time's up. So hopefully you realize for this one, this is going to be the semicircle example, where the radius is equal to the square root of 9, which of course is 3. So in other words, if I graph this, here's negative 3 over here, positive 3 over here, positive 3 over here, and you get this semicircle right here. By the way, I think I have one homework problem, just so you know, where it's like negative square root of 9 minus x squared, for instance. Hopefully you realize the negative sign is just going to make it the exact same thing, except the semicircle is a negative area down here. Just want to make sure you're ready for that. Anyways, this is a semicircle, so the area is 1/2 pi r squared, where the radius is 3. So you're going to get a final area of 1/2 pi times 9, or you can also write 9 pi over 2. And that's going to do it for that one. Any questions? Okay, now, you can go, but before you do, I just want to say thank you for coming to this summer course. It was a pleasure having all of you, even if you're watching the recording and you couldn't make it live. I wish you the best of luck in the summer. For the rest of your summer, first of all. And I hope you have a great school year, And I know you're probably looking at colleges pretty soon because you're taking calculus, for God's sake. So best of luck in your college careers as well. And last thing I want to say, just as a reminder, why did I do these 8-week summer course and why did I do it for free of all things? And I hope you remember it's because I want to be not just any tutor, I want to be the greatest tutor of all time. And so what that means is sometimes you got to start off doing it for free. As a matter of fact, when I started tutoring in 2020, during the pandemic, in the summer, no one even knew who I was. No teachers would respond to me when I would email out to them. No school districts would respond. And so what did I do? Well, of course, I worked for free. I basically posted on Facebook, on this app called Nextdoor, and I would basically take any job I could get where I was tutoring for free. And literally, it was this exact same summer course that you see now that I developed. Actually, I paid my friend to do it, who was like my best friend in high school, and I worked on the physics class while he worked on the calculus one. And literally didn't make a single penny during the summer because, again, I was working for free. And then it wasn't until the fall of that summer, so after 3 months of working for free, 6 hours a week, on top of having a 40-hour-a-week job at my engineering job, which was how I was actually able to afford this. Once I got to the fall semester, I had 14 paying customers. It was amazing. It looked like all my hard work paid off. And then also, in the spring, I had another 16 students. So I had a total of 30 students over that first year. I made thousands of dollars. It easily paid for itself. And I gotta say, if you want my entrepreneurial advice, if you want to make something big and you're starting from nothing and no one knows who you are, sometimes you gotta be willing to work for free. Because let me tell you something. When you're working for free but you love what you do, you're not really working. So the last piece of advice I'll give you, whatever you do in your life for 40 hours a week, every week, except for vacations, of course, I really hope it's something that you really enjoy doing. Because if you don't, then it's going to feel like a grind, and you're going to get beat by people who love what they do. So my encouragement to you is you can do it. I did it. I'm not that special, believe it or not. And I hope you can make something of your life and bring value to other people and make other people's lives better, like I've been doing to you. So thank you all for coming, and I hope you have a great rest of your summer. Take care, and bye-bye.